So, first of all, we should define the boundary conditions for ourselves, and we should refer back to the original equation of motion for this string. So, it will have two different equation of motion, one at this end that is attached to a mass and as in a frictionless slot, and one at this one that is connected to the spring. So, at x equals to 0, that is this end, if you call this whole length L, its equation of motion would be equals to the force into the displacement equals to ma, right? And at x equals to L, the same force that is acting onto the string into the displacement opposed by the frictional force minus kx or kw, that is the displacement. So we have the two different equation for our string at both of these ends, and we know the general solution for our vibration in strings is equals to, if you just quickly recall, that is wx into t of, that is a separation of variable method, so it can be written as a cos omega x over c plus b sine omega x over c into c cosine omega t plus d sine omega t. And so if we use this solution in equation 1 and 2, let's call it equation 1 and 2, if we substitute this solution in equation 1 and 2, so we will end up getting so first will be p into minus yeah, first we'll substitute that one, so it will be equal to minus a omega over c sine omega x by c. So we are also differentiating that with respect to x. So we are differentiating with respect to x as we are plotting in, plus b omega over c, sorry, into cosine omega x over c into c cos omega t plus d sine omega t, because that's a constant, because it is with respect to t, not x, so it will remain same. That was with respect to x, so it was differentiated with respect to x. That's all this whole equals to. This whole will be equals to m double derivative with respect to t. So now the first half will remain same while the second would be differentiated, so it will be minus m omega square. So the first part will remain same because it was with respect to x. It will be a cos omega x over c plus b sine omega x by c, and second part will be differentiated, so it becomes c cos omega t plus d sine omega t, and this condition would be x equals to 0, the whole condition being applied here. So if you substitute x equal to 0 for all of these, so you will have sine 0, this becomes 0, cos 0, this becomes 1, and then sine 0, this becomes 0, cos 0, this becomes 1, sine 0, this becomes 0, and sine 0, this becomes 0, this becomes 1, this becomes 1. Now if you just rewrite all of this expression, so you will have you will end up getting minus a minus ap plus pb omega. Oh, just take out the common. So we have minus p a omega over c plus p b omega over c into c. That's into, come on, into the c that we have here. I don't know why it's being crazy. Into c, and because this part becomes 0, equals to minus m omega square, and come on, into a and into c. So I think that's all what we have now. If you multiply c with this one, so I'll cancel out all of the c's, so we'll end up having minus p a omega plus p b omega equals to minus m omega square ac, and you can cancel out omega as well on both sides. Minus pa plus pb minus m omega ac, and that's all, I think. So we have, if you just take out that on the other side, it will become m omega ac minus pa plus pb equals to 0. I think that's all. If you take out the as common, it will become I hope we didn't miss anything here. It was minus a omega square. So sine 0 is 0, plus b omega by c cos 0 was 1. That was c cosine omega t cos. Yeah, we made a mistake here. This wasn't supposed to be 0 because it was condition for x. It will remain this same because x is equal to 0, not t is equal to 0. So what will happen, rather, both of these will be cancelled out on both sides. So we will have, because our conditions were not right, I apologize for that one. So it will be minus pa omega over c plus pb omega over c. That's it, equal to minus m omega square into a. So I hope that's all what we have. Yep. And then we can so we have pb omega over c and m omega a square. Again, this is supposed to be, that is 0, so there's no a omega c. So it is pb omega c. So I apologize for too much confusion. So yeah, now we are on track. M omega square into a plus pb omega over c. So yeah, you can write it as a into m omega square plus b into p omega over c. So that's what you have. So as a solution for this one, now you can perform the same thing for the second equation, because initially you substitute this condition into the equation 1. Now you can do the same thing with equation 2. So if you solve that one, you will end up for equation 2, substitute the same solution in equation 2. So you will have P minus omega over C A sine omega L over C. And now you're substituting here, and yeah, plus, while also differentiating simultaneously, P B omega C cosine omega L over C equals to minus K into A cos omega L over C plus B sine omega L over C. That's all we have. And yeah, now we can simplify that one. We can take it out on the other side and take A and B's separately. So you will have A equals to minus P omega over C sine omega L over C plus K cosine omega L over C plus B omega C cosine omega L over C plus K sine omega L over C equals to 0. Now we have another equation number, you can call it B, after substituting that one. So you can solve for the frequency of that one. You can solve both of them using a determinant method. So you will have, if you write A's and B's together for equation A and B, it will become M omega square into P omega by C, and then minus P omega by C sine omega L by C plus K cosine omega L over C, and this would be P omega over C cosine omega L over C plus K sine omega L over C. This whole equal to 0. You can solve this determinant, so you will end up having an expression that is tangent alpha equals to Pk minus yeah, Pmc square divided by L square into alpha square. Alpha we have defined last time. C square mk over L is whole into alpha plus P square C over L P square C over L whole into alpha. So you will have this kind of expression after you solve this one. So this is how you can find the frequency. That's the frequency equation for the transverse vibration of cable in such conditions. So that was one of the example. Let's jump to another one. Yeah. So what it states, again we have a vibration string problem as it appears. A cable between the two electrode transmission, so it's another problem of practical nature. A cable between two electric transmission towers has a length of 2000 meters, that is 2 kilometers. It is clamped at its end under a tension P. The density of the cable material is 8890 kg per meter cube. If the first four natural frequencies are required to lie between 0 to 20 Hz, determine the necessary cross-sectional area of the cable and the initial tension. So what we are going to do, we are going to use a similar method for the fix strings on both end, and that's fixed condition on both ends, and then we'll drive the natural frequency equation, and we will find all the values of area A and the T, for which we get the values of omega under 20. So first let's start solving that one. So we know the length is 2000 meters and the density is 8890, and that's a volumetric density, kilogram per meter or cube of the material. And so we have a condition that the first natural frequency should be, all the natural frequency should be between 0 to 20 hertz, and we know it's a fixed condition, as you have seen earlier. For fixed condition, the natural frequency equation is NC pi over L, so you don't need to drive again and again. If you know it's a fixed string, then you can directly write this one, and you can open up C. You can open up C, that is equals to under root of tension divided by the linear density. Tension divided by the linear density. So, and now what if we have a condition that omega 4, the last frequency, should be less than 20 hertz? Is it what it says, less than or lie between? Yeah, so it's less than equal to 20 hertz. So it means n is equals to 4. So it means n equals to 4. So 4 pi by L under root T over linear density should be less than equal to uh, 20 hertz. What it says, lie between. So basically this frequency is equals to, not the pi radians, that's the radians. So it will be equals to, if it's hertz, it will be 2 pi f, so it will be 2 pi into 20 hertz. So it should be less than 40 pi. Okay. So now we can solve it for our, and what it says, determine the necessary cross-sectional area of the cable and the initial tension. So let's solve it for the initial tension. It will be 4 pi by L under root of what you call T over the, let's make the density as same at the moment, it should be less than equals to 40 pi. So if you just take it on the other side, it will be T divided by 8890 less than equals to 40 pi into 2000, that is the length of the cable, divided by 4 pi. So it can cancel out this one, and that's 10. So we can solve it for T divided by 8890 less than equals to 10 into 2000, so it's even now greater 20,000. Now you can solve it for T, so you will end up getting, you can just take the square on both sides and then multiply on the other side. So you will end up getting tension equals to 35560 into 10 exponent 8 newtons. So that's the maximum tension that you could have at the end of the cable, to make sure that the fourth frequency is less than or equal to 20. And now consider that the permissible yield stress of the material be 300 megapascals. So now we have to make an assumption here. So let's assume that the stress, permissible stress, is equals to 300 megapascals, or you can call it 3 into 10 exponent 8 Newton per meter square, because the next condition was based on the necessary cross-section area. So assuming the diameter, and let's say the diameter of the cable is 0.1 meters, uh, so we'll have the cross-section area of pi by 4, 0.1 square. So it will end up, you will end up getting, that is 0.007854 meter square. So the permissible tension in the, considering the factor of safety as well, so that will be equals to that area into the stress. So that will become 0.007854 into 3 into 10 exponent 8. So it will become 2356 200 newtons, or 2.3562 into 10 exponent 6 newton. That is also an initial tension. So this is how you can find out the necessary tension, just to make sure that the fourth frequency lies within the 20 hertz threshold. So that's all for this lecture. I will share some similar problems for the vibration in the beams or bars, and I will try to upload some practice problem or a short video discussing the various problems in vibration of beams and bars. So you should have a look at it, and you don't have to worry about the whole calculation. Just try to understand the kind of problem you have, try to understand the boundary condition you have, and just directly pick up those boundary condition and the concerned equations from the solution that we have done before. Or if you don't have the solution directly, just use the governing equation, input the boundary condition, find out the frequency equation and the constant a b c d, and you will have your solution. So that's all for this lecture, and that's the last lecture for our semester for this subject. So should you have any question, you can reach me on WhatsApp and via email, any way you like. So I hope you have learned from this subject. It's kind of very practical nature, although there's a lot to discuss in this chapter, much in detail. But obviously, that what we discuss in bachelor's is fundamentals of mechanical vibrations, how you should approach certain problems. It has an application from the like you can say aerospace, from automobile, in the manufacturing processes, like anywhere you can think of, you can apply the mechanical vibration theory in the human body. I will share one of the model of the human body, how you can define the whole human body in terms of mass spring damper system. So that's all for this subject, and best of luck for examination. I hope you guys are safe and your families are safe. Amin. Assalamu alaikum.